Kohlrausch looked at what actually happens physically inside the solution. Let's imagine a beaker with a strong electrolyte like sodium chloride. When dissolved in water, it completely dissociates into positive sodium ions and negative chloride ions. When we apply a strong voltage using a battery, these ions start migrating. The positively charged sodium ions swim towards the negative cathode, while the negatively charged chloride ions swim towards the positive anode. This movement of ions is exactly what conducts electricity through the entire solution. But what happens as we dilute the solution more and more? Let's add infinite water. As the concentration approaches zero, we reach what is known as infinite dilution. The ions become so incredibly far apart from each other that all inter-ionic attractions completely vanish. The sodium ions and chloride ions no longer interact at all. They swim completely independently. This brilliant realization led to Kohlrausch's law of independent migration of ions. It states that at infinite dilution, the total molar conductivity is simply the exact sum of the individual ionic conductivities. Have you ever wondered why we can't easily measure the molar conductivity of weak electrolytes like acetic acid? If we plot molar conductivity against the square root of concentration, strong electrolytes like potassium chloride form a nice, predictable straight line. We can just extrapolate this straight line directly to the y-axis to find the limiting molar conductivity at infinite dilution. But look at the weak electrolyte. It curves sharply upwards as concentration approaches zero. It runs almost parallel to the y-axis and never actually touches it. Because of this massive curve, graphical extrapolation is completely impossible. We are stuck. Until Friedrich Kohlrausch came along with a brilliant physical insight. Because ions migrate completely independently at infinite dilution, we can finally solve our weak electrolyte problem using algebra. Let's say we want to find the conductivity of acetic acid. We can't measure it directly, but we can measure strong electrolytes. We take the known conductivities of hydrochloric acid, sodium acetate, and sodium chloride. By writing out their individual ions according to Kohlrausch's law, we can treat them just like algebraic equations. We add the equations for HCl and sodium acetate, and subtract sodium chloride. Look at the magic. The sodium ions cancel out perfectly. The chloride ions cancel out perfectly. And we are left with exactly the hydrogen and acetate ions. We have successfully calculated the infinite dilution conductivity of a weak electrolyte without ever needing a graph.